Hey guys, hello everyone. Welcome to Rasayan Academy once again, all of you. So we are back again with a series of practice questions on name reactions and reagents. So these questions that we do today are going to be from June 2016 and December 2016 CSIR NET examination. All right. So the first question is very simple. Let's look at the first question. So question number one, the major product formed in the following reaction is, as you can see, you are having a nitrile ester over here in the presence of light. What is going to be the product? So just by looking at this reagent, you are reminded of the photochemical reaction Barton nitrile ester rearrangement. Okay, what is this rearrangement, guys? It is also known as a remote functionalization. Okay, also a remote functionalization reaction. So what are you going to do? You're going to count alpha, beta, and gamma and delta. So this is your delta hydrogen. You have a delta hydrogen, so the bond is going to open up in this way. All right. If you want to draw it in this way, that you can do, but that's going to lead to the same thing. The delta hydrogen is going to be removed. So just like that, you can count delta and remove this hydrogen from over here. Okay. So yes, this is what you get. All right. I'm just writing the molecule in this way. The ONO bond is going to get cleaved, and you're going to get an oxygen radical, which is going to remove the hydrogen from the delta bond. This is your delta bond, delta carbon hydrogen bond. So there is one carbon radical formed, and the O has removed a proton or a hydrogen radical. This is what you get. So it's basically a remote functionalization reaction. So you are getting the nitrile group, the free NO radical is now going to connect to the delta carbon, just that you have to see. And it is present in which option? Alpha, beta, gamma, and delta. So this is at the delta position. Alpha, beta, gamma, this is at the gamma position. C is wrong, and this is only beta which is wrong, and only alpha wrong. So the correct answer is option number D. It's a simple Barton nitrile ester rearrangement reaction. Okay. And guys, we have also done many questions on the previous years. If you want, please check out those videos, and also we are going to do many more of them. All right. So also goes without saying, you have to stop by every question and then try to solve it and then see the solution. Okay. So the major product formed in the following reaction is, once again, June 2016. Now you are having a nitro compound over here. This is your alpha carbon, and the hydrogens present on the alpha carbon are going to be very acidic. In the presence of NaOH, you can just directly convert this molecule into a nitroenolate. Okay, and isopropyl CHO. So this isopropyl CHO group, this is going to be attacked. So how does that look like? Isopropyl group is going to be like this. All right, isopropyl CHO is going to be like this, and just like your enolate attacks, it's going to attack from the alpha carbon and give you an alcohol. Okay, so NO2. From here, the attack has taken place from the first carbon of the ethyl group. So you can just directly write OH and isopropyl group, just like this. Now, what is the next reaction, guys? The first reaction is Henry nitro-aldol condensation, because it is just like your aldol condensation, only driven by the nitroenolate, not your carbonyl enolate, right? And the second reaction is, by using TiCl3 and water, you are converting this carbon nitrogen bond. This is having one hydrogen, one enolizable proton. What you're going to do is TiCl3 and H2O is Neff reaction, which is the conversion of the nitro into carbonyl. Okay, this is your overall reaction. So the answer, as you can see very evidently, is option number 2. Alright, so TiCl3 and H2O is Neff reaction, converting the nitro into a ketone. Okay. Question number 39 that you see from the same June 2016 paper is, the major product formed in the following reaction is. Very simple reaction, guys. Once again, there are two enolizable protons, as you can see. from the carbon next to the tosyl hydrazone, and on the tosyl hydrazone this nitrogen is having a hydrogen over here. So absolutely you can see you have 2.1 equivalent of butyl lithium, very strong base. So whenever you look at a tosyl hydrazone and two equivalents of a strong base like butyl lithium, it could be any other base also, so don't only rely on butyl lithium. The base should be as strong as butyl lithium, right? It could be any other base also. So yes, it is going to be like this. Two equivalents is going to remove two of these acidic proton. First it will remove the NH proton, secondly it will remove one of these protons. Okay, so the mechanism works like this, that the bond is going to fall over here and the tosyl group is going to leave. Further, you have a double bond over here. Further, what happens is the minus charge on nitrogen falls over here so that you get a carbanion on the sp2 carbon. Okay, and obviously you have a source of electrophile. What is DMF? Diisopropyl amide, in this way. Sorry, this is your dimethyl formamide, like this. Yes, so dimethyl formamide, when some nucleophile is going to attack over this carbonyl, is going to remove the bond on nitrogen, and it is a source of the formyl group. Okay, so you are directly going to form this molecule over here, as you can see, CHO. Okay, this is what you form. So your answer very evidently is option number 1. Don't fall for option number 2, guys, because on the same carbon that which is having the hydrazone, let's say this one, the same carbon is going to have the CHO, which is very evident from the mechanism. So the answer is option number 1 only, and this is once again the Shapiro reaction. Alright, so guys, let's move on to the next question. The major product formed in the following reaction sequence is, so as you can see over here, that here in this in this question you see that there is a molecule, one carbon, another carbon, both of these are basically having 1,1 alkyl group, and you see that there is alpha beta unsaturated ketone. Looks like some Michael addition is going to take place, isn't it? You have a base, and the second step there is HCl. So let's try out, guys, what can happen to this molecule in the presence of a base. Okay, so in the presence of a base you are going to remove this proton from here. Yes, absolutely, this is going to form a more stable system, more stable enolate system. Alright, there's this methyl over here. Now what next? Next we do a Michael addition reaction, that is conjugate addition, in this way. Alright, so the conjugate addition takes place like this. Alright, so there's a CH3 above, you are forming a new bond. So definitely there is going to be this bond over here and O minus, but after tautomerism you'll get back the same thing. So I'm just directly writing this step. Okay, because after tautomerism you get the same thing. Alright, so once you have got this molecule, you are further going to do some reaction in the presence of a base only. And what can you see, guys? What can we see over here? That yes, you have one enolizable proton on this side, right? This is a CH3 group. Yes, over here. So you have enolizable hydrogens over here. So can you see further possibility or one more possibility of attack? Absolutely. See, let's write the methyl over here, and 1, 2, and 3. Let's write this carbonyl and this CH3 over here, isn't it? Now you can see that this CH3 can enolize, it can become CH2 minus, that is your enolate, alright, or the carbanion, and it can attack over this carbonyl. Also, that's going to give you a stable 6-member ring. 1, 2, 3, 4, 5, and 6. Okay, that gives you a stable 6-membered ring in this way. So that's absolutely a nice possibility. You have a carbonyl over here, you have a methyl over here, and in the presence of ethanol, you can protonate this O minus directly, and the E1CB mechanism is going to follow for the elimination. That is, what is an E1CB, guys? Elimination through conjugate base. This is going to follow, right? So you are directly going to get O minus double bond. Yes, guys, this mechanism is a little bit long. We are only on the first step, so we have to erase everything. Yes, and then it is going to eliminate in this case. Alright, so you finally might get something like this. Double bond O, one double bond over here, and the ring is as it is. The three-member ring is as it is. And obviously there is one methyl which we have missed. Yes, so till now the molecule looks something like this. Okay, so we have to erase everything and then we have to draw the system back again. Let's say this is what we had. One double bond over here and three-member ring on this side, one methyl over here. Alright. Now what can we do, guys? Since there is an H plus in the next step we are having only acid. So the acid is going to combine with the oxygen group, and you are going to basically draw the system in this way. Becomes OH, carbonyl becomes OH, you get this double bond over here, and there is a positive charge generated on this system, which is going to drive the ring opening of this three-membered ring, isn't it? So yes, OH, sorry, the double bond is going to be over here, alright, and this bond opens up to give you one isopropyl cation in this way, alright. So this is your overall reaction. Now the Cl minus, guys, which has attacked already, right? The Cl minus which is free because the proton is already provided, and the Cl minus which remains is going to attack over here, and this is a ring fragmentation reaction, guys. Three-membered ring fragmentation. Okay. Yes. Still writing the molecule in the same ways. Finally, you can see that elongated, this is a extended tautomerism kind of a thing which is taking place in the presence of the acid, and you finally get the molecule as option number 1, as you can see. Alright, so this is a combination of this first step is a combination of two back-to-back reaction. First is your Michael addition, and you have noticed after the Michael addition you have done aldol reaction. So this combination is known as Robinson annulation. Okay, and I have also made a video on this Robinson annulation reaction. Second step is the fragmentation of the three-membered ring in the presence of acid. Alright, so the answer is option number 1. Next question is very very simple. The major product in the following reaction is, so as you can see, guys, you are having the azide as the aldehyde group and the ester group. This is not alpha beta unsaturated, the alkene is isolated. Okay, and in the first step you have the phosphine. What is this phosphine going to do? The phosphine is going to reduce the azide in a reaction called as the Staudinger reduction. Alright, and the whole mechanism is already done. You can check it out. Staudinger reduction, your molecule is going to be reduced. Very nice selectivity question, guys. Yes, look at this. Alright, this is what you have now. Now, absolutely what's going to happen, the amine group is going to attack the more electrophilic group. Who is more electrophilic, the aldehyde carbonyl or the ester? Absolutely the aldehyde. That gives you 1, 2, 3, 4, 5 and 6 and 7 membered ring. Okay, so let's draw a 7 membered ring over here. Let's say this is your NH2 group, या फिर NH group, let's say, and this next carbon has the remaining of the molecule. Alright, and let's say this is the aldehyde carbon. So first of all, guys, you will always get the imine or the iminium ion when you are doing the attack in this way. Alright, amine reacts with the aldehyde to give you iminium ion first of all, always. And the second reagent that you have is sodium cyanoborohydride at pH less than equals to 5 is very very chemoselectively used only for the reduction of the imine bond. Okay, so you are absolutely going to have option number 1 as the correct answer. Second step is chemoselective reduction of the imine in the presence of a double bond in the presence of an ester. Right? All right, very nice question. This is once again from the June 2016 paper only. Next question, we see the correct reagent combination to affect the following reaction is. Awesome question once again, guys. As you can see now over here, you have the, you know, two fused rings. Whenever you have two fused rings, look at the stereochemistry of these fused rings. The upper phase is, as you can see, less hindered as compared to the bottom phase, right? These two rings are going to be bent towards each other, right, in this way. All right, so this is going to be a different phase, and this is going to be a different phase right over here, convex and concave phases, right? Yes, this is what you have. So the upper one is less hindered. Now what do we see? We have to convert this OH in such a way that it still remains above. So we can try out the first possibility. Let's see. NaBH4CeCl3 is once again chemoselective reduction only of the carbonyl, not touching the double bond, also known as the Luche reduction. Okay. Yes, so Luche reduction is going to transfer the hydrogen, but where? Absolutely from the top. So if you transfer the hydrogen from the top, you are going to get this alcohol below. Why from the top, guys? Because absolutely the top is less hindered. Okay, in this way it is less hindered. So this is what you get in the first step. In the second step, you are having Crabtree's reduction, hydrogen and iridium based catalyst. So this is a Crabtree catalyst, and it is very very chemoselective and specific to give you reduction on the same side of the alcohol. All right, so the reduction is going to take place on the same side as the alcohol. It is a chelation controlled reduction. Okay, so where is the alcohol? Alcohol is below, so the hydrogen is also transferred below, right? So we are just going to write it in this way, that the alcohol is below. Your methyls will get above, guys. Be very careful about this. The methyls will get above if your hydrogen is transferred below. Okay. Yes, this is exactly what we have, but we still don't have the product as of now. Now, the best way of converting this OH to above OH is absolutely Mitsunobu reaction. So this is it. Phosphine and carboxylic acid, dead molecule. Fourth one is the reduction of the ester that forms from the benzoic acid, Mitsunobu reaction. So you will get the product after this, Mitsunobu reaction, and the reduction of the ester which is formed. Very very easy and absolutely beautiful question, once again from June 2016. Also, guys, another question is a correct match for the following transformation from P to S for process 1 to 4 is. As you can see, very simple question this is. You just have to take some time and do this peacefully. So we have already done all of these reaction: Diels-Alder, Norrish type 1, photocycloaddition followed by Diels-Alder, and Norrish type 2. So as you can see that option number 1, you are having alpha and CH2 and CH3, because the ethyl can be broken like this: CH2 and CH3, alpha, beta and gamma. If you see a gamma hydrogen over here, so absolutely this is going to be the Norrish type 2 reaction. Okay, if you see a gamma hydrogen, guys, that is going to be Norrish type 2 reaction when a gamma hydrogen is present. Okay, and you can do this mechanism, you are going to get the same thing. So P is going to match with 4. Okay, in option number Q, you don't have a gamma hydrogen and it's only your ketocarbonyl, so the alpha cleavage has to take place followed by decarbonylation and radical dimerization to give you this molecule. So Q has to match with 2, which is Norrish type 1 reaction, alpha cleavage. Okay, Yes. What about R and S, guys? The S molecule, if you check out very simply, that this is your oxygen, double bond oxygen. This is a simple Diels-Alder reaction taking place between the molecule, all right, between the more electron rich ring, because there are two rings. We are going to take the more electron rich ring as our diene system, and the oxygen absolutely is your dienophile. You are getting a Diels-Alder reaction over here. So S is going to match with 1. All right, let's see if that can be done. And what about R? What about R over here, guys? Let's see what is happening. It looks like more than a simple Diels-Alder reaction, isn't it? So photocycloaddition followed by Diels-Alder reaction. Let's see what is happening. So if we see photocycloaddition over here in this way, which means 2 plus 2 cycloaddition, because in the presence of light, 2 plus 2 cycloaddition is more favored, isn't it? Yes. In the presence of light, 2 plus 2 cycloaddition is more favored. This is what you have, and on this side of the molecule you have generated a diene system which can react with one more anhydride molecule which is present over here to give you one more reaction. So this part of the molecule is coming from the 2 plus 2 cycloaddition, and this part of the molecule is coming from the Diels-Alder reaction. So R matches with 3. Answer is option number 3 over here. Okay. Next question is very simple once again. As you can see that there is an alcohol, allylic alcohol present over here, CH2I2, zinc copper couple. This is your Simon-Smith reaction. Alright, so let's check it out what is happening over here, guys. In the Simon-Smith reaction, always remember that if your OH is above, you will also do the cyclopropanation above. That is, it is also a chelation controlled reaction. Let's say we have formed a molecule like this, where the cyclopropanation takes place on the same side as the alcohol. Okay, which means the hydrogens are going to be below. Absolutely. And what is the ruthenium reagent? Ruthenium and NaIO4 is going to do the over-oxidation. That is basically it's going to give you the acid over here, right? On this carbon, it's going to give you the acid, right? So absolutely it's a very simple reaction, Simon-Smith reaction, but here the stereoselectivity is important. Chelation controlled reaction followed by the oxidation of alcohol into primary alcohol into acid. Okay, this is your answer, option number D. Now the similar question asked in December 2016. The major product formed in the following reaction is, you are having the zinc copper couple and CH2I2. So which alkene is going to be basically cyclopropanated, which is again very simple, guys. Why? Because zinc copper couple reacts with only electron rich alkene. This alkene is in conjugation with the ester, so it is not going to be used, and we are going to eliminate this product possibility as well as this. No epoxidation. This is not your Korachkovsky reaction, and this is obtained from the Tebes reagent. We don't have it, so it's wrong. Option is D, where we are doing the cyclopropanation on this molecule, right? This is your correct answer. Last question, guys. The major product formed in the following reaction is, now this is a benzoin condensation reaction, as you would see, right? And the correct answer is option number B over here. Just try this out. Benzoin mechanism, this thiazolium catalyst that you are taking over here, on this carbon you are going to have the negative charge, all right, and it is going to basically uh, work just like your cyanide, all right, just like your cyanide, and also very similar to the Stetter reaction. Okay, so you can check out the video of Stetter reaction. This is going to be your uh, the same reaction over here taking place, right? Yes, and we have one more reaction over here, 118, as you can see. So this is going to be once again the Barton nitrile ester rearrangement, guys. You have checked out alpha, beta, gamma and delta. So this delta carbon is away and it is above from the nitrile. However, alpha, beta, gamma and delta, this delta carbon is on the same side as the nitrile ester, you can transfer the nitrosyl group very easily on this carbon. But in the products you don't see a nitrosyl directly, because when you transfer the nitrosyl, when you write the nitrosyl in this way, you can also do tautomerism and you can write the oxime, and oxime in the presence of acid will finally give you carbonyl. Okay, so the answer is option number A. This was your last question, and I will see you very soon in the next video. This question was from the December 2016 paper. All right, bye guys, everyone. I'll see you very soon, and also keep practicing. Bye guys.